In this MindBite, we look at the propagation of signals along transmission lines. Now, a transmission line is a propagation channel that can carry electromagnetic waves, importantly both in the forward direction and a backwards direction, either bidirectional. The important thing that distinguishes a transmission line from a circuit is that transmission lines are long compared to the wavelength of the propagating wave. So for instance, if you're propagating at a high frequency such as 300 megahertz, then if a circuit is more than say half a meter across, half a meter to meter, then the size of the circuit is of the order of a wavelength of a signal. Therefore, the voltages will be different in different parts of the circuit because they'll be separated by a sizable fraction of a wavelength. So the oscillation will go from a maximum to a minimum over half the wavelength of the propagating wave. Electromagnetic signals can propagate in one of two different ways. Either we can be dealing with an electromagnetic wave like light or a radio wave, which can propagate best through a pure insulator, or it is a conduction wave. It's a wave of a movement of a concentrated area of charge, generally carried by electrons, and so you get a compression wave of electrons travelling along a conductor, and the more conductive it is, the better. Now at high frequencies, then signals tend to propagate predominantly as electromagnetic waves through insulators, and at low frequencies they tend to propagate as conduction waves through conductors. The signals we'll be dealing with are generally those of propagating electromagnetic waves inside insulators, so such as a radio frequency wave travelling along a coaxial cable, where there will be a small conduction component in the central wire and the sheath, but most of the power is carried in the electric and magnetic fields in the insulation in between. Now, a very general model of a transmission line can be made out of lumped components, such as in this figure, where a section of transmission line has so much resistance per unit length due to the materials that the transmission line is made of, some inductance per unit length due to inductance with materials around the transmission line. There's a small amount of capacitance between the forward and return route of the transmission line, and there may also be some leakage through the conductor. This is a very general model of a transmission line. You can think of a transmission line being made up of a very large number of short sections have these properties of inductance, capacitance, resistance per unit length. Now, once you have a transmission line which is longer than a sizable proportion of a wavelength, then you need to model your signal as waves propagating in the forward direction or the backwards direction. Now, you can express these voltage and current waves either in phasor form, where the temporal oscillation has been removed, or as a function of position and time, where the variation with both space and time are included in the phase components of the cosine and the sine. So in this case, where you have a negative sign, a minus sign between the time and the space, this indicates a wave that is propagating in the positive x direction. It looks like a cosine profile which is sliding along the x-axis in the positive x direction, and that's the same for the voltage and the current in this case. Such a wave moves with a phase velocity, which is the speed that a point of constant phase moves. So for instance, a point of constant phase could be a zero crossing or a maxima or a minima, and if you track one of those, it will be moving at some speed, and that speed is given by this ratio of the angular velocity to the wave number. Now, for the signals and conduction paths that we're dealing with, a signal will typically propagate at about half to 2/3 of the speed of light in free space. Now, the speed of light in free space is about a foot a nanosecond, so typically our signals will propagate about 20 centimeters in 1 nanosecond. So for instance, your laptops and computers will have clocks that are going through several cycles per nanosecond, and during a single cycle a signal will only propagate a short distance across your computer, about the distance from the Q key to the T key, for instance. Now, when you have a transmission line with a voltage and current wave traveling along it, then at any point in the line you can define the ratio of the voltage phasor to the current phasor. You'll remember a phasor is a complex number that describes both the amplitude and the phase. This ratio, called the characteristic impedance, is a constant for a transmission line. It's the same wherever you measure it. It has the opposite sense when you're dealing with a backwards travelling wave, hence this minus sign in the definition. And that's due to the direction that the current is oscillating in. The voltage wave is in the opposite direction. Really, to understand why that minus sign is there, you need to understand the way that the magnetic fields are produced, and that is beyond the scope of this course. The important thing to remember is that the characteristic impedance, although it's a ratio of a voltage to the current, it's not an actual impedance like a resistance in a heating element of a kettle, because it does not cause ohmic heating. Now, most of the cables that you'll see for radio waves have the characteristic impedance written on them. And a typical characteristic impedance is about 50 ohms. So 50 ohm cable is quite common, but that doesn't mean it acts like a 50 ohm resistor and that it doesn't generate heat when you pass current through it. So although it's a ratio of voltage to current, it is not an ohmic loss. If you think about this lumped circuit model for a transmission line that we saw earlier, this is the model where a short bit of transmission line is represented by lumped components of the resistance, inductance, capacitance and conductance per unit length, as in this diagram here. The resistance in the line will cause ohmic heating, and that will lead to losses. The voltage and the current will reduce as a wave propagates a line where the resistance is non-zero. Similarly, if this conductance path between the forward and backward conduction routes is non-zero, then some of the signal will leak through this conductance before it gets to the end of the transmission line. So once again, the voltage and the current will decrease as it propagates. So for this reason, cables are engineered to be as lossless as possible. This resistance and this conductance are made as small as they possibly can. And in that case, the characteristic impedance is the ratio of the inductance to the capacitance per unit length. And it is a real number. If there is some resistance or conductance there, then the characteristic impedance will become a complex number, and the imaginary part will tell you how quickly the signal loses power as it propagates along the line. But in all the cases that we'll look at, we'll be treating transmission lines like they're lossless, so the characteristic impedance is a real number. Now we've looked at the expression for waves travelling in the positive x direction. Waves travelling in the negative x direction, which we think of as travelling backwards along the transmission line, differ only in that they have this plus sign in the phase expression for the cosine and sine components at a particular frequency. So these expressions are for cosine and sine patterns which over time slide in the negative direction along the x-axis. Now because our transmission lines are bidirectional, typically they have signals propagating both in the positive direction and the backward direction at the same time. There are some ratios we can define. We've already seen that the characteristic impedance is the ratio of the voltage to the current of the forward propagating wave. Wherever your transmission line goes through a sharp change of characteristic impedance, you'll get a point that reflects some power. So if you have a wave propagating in the forward direction along a transmission line and it reaches the end where it's either a load or it joins to a different sort of transmission line, then at that point you'll get some reflection, and some of the power will bounce off that point and turn into a backward travelling wave. We can define a voltage reflection coefficient, also known as a scattering parameter, also known as an S parameter. It can be defined to be the ratio of the backward travelling phasor to the forward travelling phasor, and that could be either voltage or current, but once again a minus sign creeps in if you're dealing with current. So typically you have a forward travelling wave with a phasor V+, and at the end of a transmission line where it joins a load such as an antenna, some of the power will bounce off and produce a backwards travelling voltage wave, and the ratio of the backwards to forwards travelling voltage wave phases is this reflection coefficient. Now in a lossless line, where the voltage and current phases only change in phase as they travel along a transmission line, the amplitude doesn't change, then the size of the reflection coefficient is the same wherever you measure it along the line. The power in the forward travelling wave is proportional to the amplitude squared. It has this expression in terms of the voltage phasor or the RMS voltage value. So we can define a ratio of the forward travelling power and the backwards travelling power. Simply by squaring these phasors, we can see that that ratio is equal to the reflection coefficient squared. So because the amplitude of the backwards travelling wave is this reflection coefficient times the amplitude of the forward travelling wave, therefore the power in the backward travelling wave is the reflection coefficient squared times the power in the forward travelling wave. Now, just by conservation of energy, if gamma squared is the proportion of power that bounces off this point, then the power that continues is 1 minus that. So you have an accountancy here of the power. Say you have a power of 1 propagating in the forward direction, a proportion gamma squared bounces off and then propagates in the backwards direction. The rest of the power, the remaining proportion of the power, which is 1 minus gamma squared, must propagate forward into the load. Now we derive an expression for the voltage reflection coefficient in terms of the characteristic impedance and the impedance of the load at the end of the transmission line. Now we know the load, just an impedance, ZL, has a ratio of the voltage to the current, which is given by just this impedance, ZL. Similarly, the total voltage at a point is a combination of the forward and backwards travelling voltages, and the current is the combination of the forward and backwards travelling currents at that point. Now, using our definition of characteristic impedance allows us to write an expression for the voltage reflection coefficient just in terms of the ratio of the load impedance and the characteristic impedance of the line. This expression is usually rearranged to give you an expression for the voltage reflection coefficient in terms of a normalized load impedance, which is the load impedance divided by the characteristic impedance of the line, and it's given by this expression here. There are 3 cases it's worth remembering. The first case is what happens when a transmission line ends in a short circuit. In this case, the load impedance is equal to 0, and putting 0 into this expression gives you a reflection coefficient of -1. Now this is because there's no voltage across a short circuit. Therefore the forward and backwards travelling waves have to be in complete antiphase, i.e. the backwards travelling wave is the negative of the forward travelling wave at the short circuit to give you no voltage when you add them together. Case 2 is for an open circuit. In this case the forward and backward travelling waves are the same at the open circuit, and so the reflection coefficient is equal to +1. Now, an open circuit corresponds to a load impedance which is infinite, and in that case the -1 and the +1 become irrelevant and the ratio is just equal to 1. The special case, and the case we're often aiming for as radio engineers, is called a matched termination. And that's when the load impedance is equal to the characteristic impedance of the line, i.e. the top line of this expression is equal to 0. Therefore our reflection coefficient is 0, and all the power in the forward travelling wave then enters the load. This is the case we try to produce. If you imagine a transmission line taking a signal to an aerial to be broadcast, you want all the power in the signal to enter the antenna and be broadcast. You don't want any of it to bounce off and go back into the transmitter. So we're always aiming for a matched termination at the end of our transmission line. Now the voltage standing wave ratio is a measurement that's commonly made to determine how well we've achieved the matching of a transmission line, the load it's intended to drive. At any point, the voltage in the line is the combination of the forward and backward travelling waves. At the load, that sum is the forward travelling wave plus the reflection coefficient times the forward travelling wave, because that's equal to the backwards travelling wave. And so at the load, we experience a voltage that's oscillating with an amplitude of 1 plus the reflection coefficient, where the 1 is telling us about the forward travelling wave and the reflection coefficient is telling us about the backwards travelling wave. As you move away from the load, then the relative phases of the forward and backward travelling waves change, and at some point you're going to get to a point where the forward and backward travelling waves are in complete phase, and so the 2 amplitudes add. If you move slightly further, then the forward and backward travelling waves will be in antiphase, and so the amplitudes will subtract. The maximum voltage oscillation you get along the line is when the forward travelling wave and the backward travelling wave are in phase, and in that case you just add the amplitudes, where the amplitude of the forward travelling wave is the modulus of the forward travelling wave, and the amplitude of the backwards travelling wave is the size of the reflection coefficient times the forward travelling wave. Similarly, if you move slightly further away, then the forward and backward travelling waves will be in antiphase. And in this case, the total amplitude is the amplitude of the forward travelling wave minus the amplitude of the backwards travelling wave, where the amplitude of the backwards travelling wave is given by, once again, the size of the reflection coefficient times the size of the forward travelling wave. The voltage standing wave ratio is the ratio of the maximum to the minimum. Because the maximum can never be smaller than the minimum, this ratio is always bigger than 1. So voltage standing wave ratio is a ratio between 1 and infinity when the minimum value goes to 0. You can measure the voltage standing wave ratio using a slotted waveguide just by moving a probe along a piece of transmission line to measure the maximum and minimum voltage oscillations. To demonstrate how sensitive the voltage standing wave ratio is to reflected power, consider the case where the reflected power is 1% of the incident power. In that case, the size of the reflection coefficient is 0.1 because the size of it squared is equal to the proportion of the power that's reflected. The voltage standing wave ratio is much bigger than this. It's 1.2 because the size of the reflection coefficient affects both the top and bottom line of our expression. So this is quite an easily measurable voltage standing wave ratio, and yet it corresponds to the case where only 1% of the power is reflected from the load. So as an example for all this, consider a transmission line, a coaxial cable in this case, taking a television signal, one of two television sets. Television set A yields a voltage standing wave ratio of 5.8, while television B yields a voltage standing wave ratio of 1.5. Which is the better television set to use? So which combination yields the most signal going into the television set? Now we can rearrange our expression for voltage standing wave ratio so that we can calculate the reflection coefficient from a measured voltage standing wave ratio. Using this expression, we find that for television set A we get a reflection coefficient of 0.71, but for television B we get a much smaller reflection coefficient of 0.2. The proportion of power that is reflected is these values squared. So we see that 0.5 or half of the incident power is reflected off television set A, whereas only 0.04 of the incident power is reflected off television B. So 50% of the incident power is reflected off television set A, while only 4% is reflected by television B. Therefore, television B is our preferred option.